So we're back again with some implementation. I have prepared files for you in Moodle. That's this Thermo-Canti-Dyn, obviously a dynamic example. The Thermo-Canti lever, that's a static example. There is a post-processing Python file and also the element template. As usual, we will start with looking at the problem file here, and yeah, let's directly look into the results rather than talking about the boundary conditions, because I think it's easier to see them and you know how to read this anyways. So if I start this file, I get some plots. Okay, of course, I have made the implementations that are required to see this. And therefore, I have used here my final element, but you know the procedure by now, right? So you you modify the template name here and add the name in this line. Okay, what are we looking at? We are looking at a cantilever. Here, two plots are presented. The left-hand side is a plot of the cantilever in the deformed state, as well as in the right-hand side. But we have on the left-hand side the temperature as a counterplot, and on the right-hand side a von Mises stress plot. Von Mises stresses are a scalar which can be computed from the stresses, and I hope, as you're all engineers, that you have a clue what this means or why this is interesting to you. Otherwise, please look into Wikipedia. So we will implement actual post-processing tasks for these color plots also. So what we see is the cantilever is clamped here on the left-hand side. This is actually the boundary condition that we prescribed. And here from the temperature plot, we can also see that it is a little bit hotter on the bottom in this range and colder on the top here in this range. That's also introduced through boundary conditions. So I prescribed a certain temperature increase degrees of freedom as an essential boundary condition in this section here, and the same with a negative prescribed value on the top. And all the deformation that we see here stems from the temperature gradient within the cantilever, which leads to bending. Yeah, so the material here in this section where it's a little bit hotter, it will expand, and on the top here it aims to contract, and due to this we get a bending phenomena. Also, we see some stresses here. So the von Mises stress plot here indicates that there are stresses present in this cantilever, and this is, I hope also everyone can imagine that there are some stresses involved, because yeah, as I said, there's a gradient also of contraction and expansion, while the complete side here is, for example, fixed on the support. So there we restrict any deformation, and all of this leads to some stresses occurring here in basically the center of the cantilever. Right, I think everyone has understood this problem so far. Let's take a look at something else. You might have recognized here that I used lots of Newton iterations. I hope I deleted, so the version I shipped to you has only 2 of them. But this is what I said just as an example. Of course, I have the right tangent also implemented, but here I switched the right tangent off. So I'm working with just modifications to the right-hand side. That means I have only changed the definition of the stresses here. Of the stresses. And that leads me to this kind of residuals. Sorry, I can also enlarge the whole font here a little bit, so that's easier to see, I guess. So let's take a look at my residuals. First, I got here something with 190, and then yes, I'm getting closer to 0, but with this 1.2 here as the second residual, this would be something that is not correct which definitely gives me the hint that your implementation of the tangent is not correct. So once more, this is a no-go. I'm just showing it here to give you at first the opportunity. By this you can check the implementation of the stresses, whether this is correct, because if you do this without modifying the tangent in the first place, just modifying the formula for the stresses, you should see the same deformation that we just looked at. So that's something that you can test your stresses and then focus on the implementation of the tangent correctly. But the tangent need to be implemented correctly in the end. You can also see that the next value here, 10 by the power of 12, is our approximate zero. And you can also see that with performing further Newton iterations, there is not changing in this zero anymore. So this is as far as you can get also with a perfect tangent here in this case. Okay, what's new with respect to this boundary value problem? We have an extended number of material parameters. All of them were discussed in today's session. We have U, X, and UY as degrees of freedom, here used by name for placing the essential boundary conditions. We have the temperature increase degree of freedom, which I named here capital DT. And that here is our bottom temperature increase, and this is our enforced top temperature decrease. Okay, anything more that we should look at? Yeah, the plot here is a little more complex, but that should just give you some more examples that you can use later in your implementation. Let's take a look what to expect if you implement the uncoupled case first. So the whole coupling can be switched off by modifying one material parameter, which is alpha T. Alpha T or alpha theta is our heat expansion. So if the material has no heat expansion coefficient, there is no coupling in the sense that we implemented it. So if I rerun this example with switching this guy here to 0, that's also an interesting aspect. Yeah, you see no deformation. However, still the temperature distribution is there. This is because the balance of energy is completely implemented on its own. So if you apply cool temperature here and hot temperature here, the temperature distribution will be calculated using balance of energy and is already correct. The only thing is that here with respect to the displacements, there is no displacement load. There's just this zero boundary condition here. So for the balance of momentum, there is nothing to calculate. Also, no stresses arise at all. This is why we have 10 by the power of minus 14 here on the von Mises stress bar as well. You can, however, introduce, like, let's, as usual, play a little bit. Here at the end of the bar, I introduce some pointing upward force. And if I hit run, we see nothing. Ah, the bar is not 20 in length, it's 10 in length. Okay. And let's say we don't make that much of displacement. We do it this way and run again. So the boundary condition I prescribed had no effect because I targeted it to any node located at x20. Bar stops at 10, so there was my mistake. Okay, so here we have again, or we have a deformation, which is due to this central boundary condition. Actually, it's not a force here, it's like as if the tip was actually displaced in y direction. This, of course, leads to stresses. Bending behavior is physical as we expect from a correct balance of momentum implementation. The temperature distribution is still the same because both are uncoupled. So that's just what to expect. And the last thing that we see from this example is with an actual zero coupling because of heat expansion equal to zero, we are directly landing here at our approximate zero residual also within the second iteration. Great. So I hope this works as well. So here we have a dynamic problem. I'm doing only 2 Newton iterations here, so we will not get the very correct solution. You must not do this. I'm just doing it here for not modifying my element anymore because the behavior will be similar, but technically what I'm doing here is incorrect. With a non-correct tangent, just 2 Newton iterations is completely wrong, right? We have a very similar setup. That's the one that I not showed in Moodle, I guess. We will take a look at the movie in a second. The only thing that I'd like to mention here is I'd like to show you an additional skill that you will find useful for your projects. If you make a parameter study or convergency study, that means you run a simulation and at the end you have a plot of, for example, your displacement over time. This result until now was lost, right? If you do 10 times this simulation with 10 different results and you want to combine all these results into a single plot, this is a challenge at this point. So here is a solution. So this bar is like actually length 20 and it's clamped on both sides, and we introduce a gradient which will make the cantilever swing a little bit. Also, we have a load function here, which is not just 1, but we introduce this gradient for up to 1 second, and then we release it. We will see the response in a second. But from this, there is deformation, which I record here in the usual way. And I have it saved in, so the y displacement in the middle of the bar is saved here in a field UYS. UXS is the x displacement, and also I record here the time steps. So that will leave me with the opportunity to plot the y and x displacement of this point in time. You can see here on the bottom, I use a feature of NumPy to save this data. Syntax is name of the file that you want to save it into, and then the name of the array you want to be saved in the file. How to load this, we will take a look at in the post-processing file in a second. So I hit run. And this is the response here. So we see that this gradient is applied here. Due to this gradient, we again introduce some bending here. This cantilever is clamped here only in y direction, so it is free to also be a little bit elongated in x direction, and that leaves this unsymmetric behavior of this cantilever. We are now after 1 second, so the temperature gradient is not enforced anymore by the boundary condition. And so we can see that the temperature kind of evens out through the cantilever. However, still some oscillations are present. But the main aspect here is, once more, we have just introduced temperatures or a temperature gradient in this body. And due to this, we get this mechanical response. That was the last time step. So I close this. And after running this example, you should be seeing in the same folder here those NumPy files. Those are generated from these commands at the end. You will not be able to read them because they are usually stored by default in a binary format to save some space. But let's have a look at this post-processing file. So here we load the data back into the game, and the data can be saved from multiple simulations. Here it's only one, but you can do this multiple times. However, each data that you save needs its unique data name, that's for sure. And then you say numpy load to reload this data from the file name. Now you need to specify the ending npy1. And this is on the left-hand side of the equal sign here, you need to provide a variable name to save the data into. And this plot here is very much like the plots that we had before. So I'm simply plotting here our reloaded y displacement over time and x displacement over time with some neat modifications. Let's run the file. And this is the plot that I get with a certain plot title, with a legend here, with different colors for the different curves that I see inside this. I have axis legends and I have some specified limits for my x and y axis. Yeah? I'm giving you this now so that you have the opportunity to produce, let's call them quality plots for your final presentation. It's obviously very easy to see how much effort was taken to produce nicely looking plots that just delivers the message that you want to deliver. Feel free, here I put the link down below to indicate that there is this website from Matplotlib which gives you a lot of examples, and you can just look at the examples and choose anything that you feel could benefit also in your presentation in the end. One thing that I might forget to mention here, for this non-dynamic example, all the dynamic material parameters are set to 0. Obviously, for the dynamic example, however, we have set, for example, a density. In this case, no damping, also no body forces. But here, for example, C, our heat capacity, specific heat capacity is also there again. As usual, feel free to play with these values to get a good feeling how they behave once you have the implementation done. Speaking of implementation, let's take a look at, at the element template. Okay, so we combine the field of temperatures and displacements. That, first of all, means we have to state one more degree of freedom per node. Mentioned before, I used the name capital DT here for our delta theta. Also, we need to increase our history field. So before we had per node 3 times, so acceleration, the value itself, and velocity, 2 in case of the balance of momentum for displacement in x and y direction, and 1 in case of the balance of energy for the temperatures. So we now combine those, so we have 3 times 3 times 3 number of history variables. We have extended the name of the material parameters, or the list of the material parameters, to the ones that we talked about today. And I have introduced here some more names for the post-processing. This is T, where T should be the absolute temperature, not the temperature increase, but the absolute temperature. And sig Mises is the von Mises stress. Let's take a look at the element subroutine. So here we see R and K are of size 4 times 3, because now we have 4 each node, 3 degrees of freedom. The list of material parameters read into the problem here. And then we have a certain structure to read in the values from the UL field. I arranged this already for you so that you can use the UI field as before. And DTI is basically the same as TI, just in that this is now the increment of the temperature. I have also prepared for you reading the history fields and writing to the history fields. Of course, I know it's a lot of copying, but you need to implement the new mark time integration as done before. Now, with respect to the solid fields and the energy fields, so temperature and displacement. Then we have our Gauss integration loop, same as before, because the element has not changed. Also, the shape functions have not changed because of the same topology. So I left that inside this element. And then, of course, in between here, a lot of must be happening. And in the end, you have to prepare the element vector and the element matrix. So this is basically where you really need to take care. All the other calculations before, they are really almost the same, of course. And if you introduce the coupling, that must be there you need to make some modifications, but everything else is basically copy and paste. At this point, it's also copy and paste, but you need to really think about where your previous lines of code now need to be located. Are they here in the spot, like this is the third entry per node I for the right-hand side, or in the first one, for example? Of course, 1 and 2, these lines here will carry the implementation for the balance of momentum. This line, the balance of energy. And we have seen also before that you might need to make some loops here and also some statements outside the loop so that you do the integration right. You see, complexity raises with the stiffness matrix here, with the element matrix. You don't need to preserve all these lines. You can do it completely with loops and the few statements outside the loop. So this is just to and kind of, I think this is also kind of the answer to the question at the beginning of me talking about implementation here. This is where you need to make the changes. Yeah, and of course, also here, like you need to locate the terms in the correct spot. I highly encourage you make a lot of comments, make a good structure like comment, implement balance of momentum first term, bam, implement balance of energy first term or second term, like make good comments, because if you have any problems, if you need to debug, if you need my help, this makes it a lot easier, right? Because lots of you use different variable names to store your variables, and this here helps them to figure out where the issue is. Okay, the post-processing subroutine here is also important, because like this is not, let's say this is not required 100%. Yeah, the element will run without implementing the stress plot, but it's just nice and will be accounted for when we think about your marks. So what's already implemented here is the absolute temperature output that you see here. At a certain point, this routine exports nodal values for the requested field. So the nodal values for the absolute, for the absolute temperature are the degrees of freedom, which are your delta T. But for the absolute temperature, we need to add T0, so the theta 0 on top of it. So this line is straightforward to understand, I guess, and it's already done. But the same idea of exporting nodal values applies to the stresses. Luckily, this is kind of also done for you. So you see here in this line, this computes nodal stresses from Gauss point stresses. So what you're asked to do in the post-processing step is to compute for, see here, the Gauss loop, at each Gauss point, the von Mises stresses. That involves computing the stresses in the first place. This is exactly the same as in the KS subroutine. So you can, once the KS subroutine works properly, you can copy over all the code. Inside this Gauss loop here, compute the stresses, then look into Wikipedia, get the correct formula for the von Mises stresses, and then insert this in this line. Leave that line and everything works out of the box. Of course, there's this sanity check here, and due to the comment from one of you guys last exercise, I also make corrections to the template so that this can be run. And of course, it does not run. Why not? Verbose is not defined. Okay, I see. So if you're facing that error, that belongs to not this, but the other Gauss loop. Yeah, it belongs to this plot here. So this must be deleted. Then this element file as it is can be run as well. And as you see, you can get a response here, which we can use for debugging. Whew. Okay. So before I ask for your questions, let me formulate what I'd like you to do. First of all, take this element and implement individually the balance of momentum and the balance of energy. If this works, as I said, you can run this, this Thermo-Canty example. Then without the coupling, you get the response that I got here from setting alpha t to 0. And see whether the fields work as expected, so that you have not messed up with putting the same equations into the right spot for element, vector, and matrix. That's the first task. Second task would be, and you have, I guess, 2 weeks now for doing this, make the derivations on your own. For the project, we will ask you to give at least a summary of this derivation anyway. So sit down. As I said, start with the balance of momentum. Bear in mind that now sigma has also some dependencies of delta theta, and do the steps as we did together in this exercise. The steps are basically the same, just the results are a little bit different. If you have done that, you probably know how to implement also the tangent. However, first start with implementing the different stress response. As I said, this will involve computing the temperature increase at the integration point using standard interpolation formula here and implement the stresses. Using some more Newton iteration, figure out whether you did it correct. Yeah, the response should look like the one I provided in Moodle. And if this works correctly, then try to implement the correct tangent parameters. As usual, ask me for any help if you feel like you're stuck. And yeah, as usual, write me an email. We can arrange an appointment, or sometimes solving in an email is also possible. Yeah, but until I guess, as I said, this is the last input. If you accomplish all the tasks, you're basically done with this course, except for finishing the homework that I gave you, so that I can arrange the correct groups for you, and then yeah, prepare the project and yeah, pass the colloquium in the end. That's like all the horizon for this course. Of course, yeah, regarding the time schedule, as I said, we will see us definitely in 2 weeks. So there's 1 hour, one exercise session where I'm completely here just to answer questions and help you with your implementation anyways. Still, there's the opportunity to ask me via email for any help in the meantime. And after that, until we we have the groups formed, which should be the case in 2 weeks. And also we can then arrange appointments for your colloquiums. Those appointments we can arrange with you together so that we are a little flexible, so we can make sure that there's enough time for all of us or that the appointment suits to everyone. One more thing so that I don't forget, in the Moodle course, there is here this course feedback, which is the evaluation of this course. So I hope this looks a little different for you than for me, because I'm a teacher. But as you see, this is the standard form. So the examination office or the office that takes care of this asked us to implement this in Moodle. So yeah, we are of course happy to get feedback, especially for this online course. So if you feel like there's something that you want to say for this special format, I'm actually really interested in your feedback in this sense. So leave some notes in the notes section there. I will definitely read it. It's of course it's anonymous. So especially as you write it in with your keyboard, we cannot identify any handwritten language like fonts. So it's even more anonymous than usual. Okay, so I think I stopped the recording for today, and then we have still some time for question and other aspects. Okay.